Dear student, today we are going to learn the topic of Science 1, that is lenses. We are using lenses in our day-to-day life. Lenses are used in spectacles. Lenses are used by old person for reading. Watchmaker also use the lens which he attach to his eyes. Lens is also fitted in the front door of the house. The lenses are also used in telescope. A lens is a transparent medium which is bound by two surfaces made up of either glass or fiber. If the two spherical surfaces are bulged outward, it is called convex or double convex lens. This lens is thicker at the center as compared to edges, and the lens in which both the spherical surfaces are curved inward are called concave or double concave lens. This lens is thinner at the center as compared to its edges. It means there are two types of lenses, convex lens and concave lens. When a ray of light passes through the lens, it gets refracted twice, once while entering the lens and once while emerging from the lens. The direction of rays changes because of this refraction. Both the surfaces of most of the lenses are part of a sphere. The surface 1 is a part of sphere S1, while the surface 2 is a part of sphere S2. Now let us learn some parts related to lenses. Center of curvature. It is denoted with the letter capital C. A lens with both the surfaces spherical has two center of curvature C1 and C2. The centers of a spheres of which lens is a part are called center of curvature. Radius of curvature. A lens with two surfaces have two radius of curvature R1 and R2. Principal axis. The imaginary line passing through both the center of curvature is called principal axis of the lens. Optical center. O is the optical center of the lens. This is the point inside the lens on the principal axis through which light rays passes without changing their path, and it is called optical center. Now let us learn principal focus, which is denoted with the letter F. When light rays parallel to principal axis fall on a convex lens, they converge to a point on the principal axis. This point on the principal focus is called principal focus. Convex lens has two principal focus, f1 and f2. As the light rays parallel to the principal axis converges in a single point, the convex lens is called converging lens. While the light rays parallel to the principal axis falling on convex lens go away from one another after refraction, so concave lens is called diverging lens. The ray falling parallel to the principal axis of concave lens diverge after refraction in such a way that they appears to be coming out of a point on a principal axis. This point is called principal focus of concave lens. F1 and F2 are the principal foci of a concave lens. Now we'll learn what is focal length. The distance between the optical center and principal focus of a lens is called focal length. We can find the focal length of a convex or concave lens by a simple experiment. Keeping the position of screen fixed, obtain the clear image of distant object like tree or a pole or a building with the help of lens on the screen. Measure the distance between screen and the lens with the help of meter scale. Now turn the other side of the lens towards the screen and again obtain the clear image of the distant object on the screen by moving the lens forward or backward. Measure the distance between the screen and the lens again. The image of a distant object is obtained close to the focus of the lens. Hence, the above distance is the focal length of a lens. Thus, we can find the focal length of a given lens. Now, let us learn a ray diagram for refraction. We can obtain images formed by lenses with the help of a ray diagram. From this ray diagram, we can obtain the position, size, and nature of the image. So let us learn the three rules for drawing ray diagram for the image obtained by convex lenses. So the rule number 1 is when the incident ray is parallel to the principal axis, the refracted ray passes through the principal focus. Rule number 2. When the incident ray passes through the principal focus, the refracted ray is parallel to principal axis. Rule number 3. When the incident ray passes through the optical center of the lens, it passes without changing its direction. Thus, we can determine position, size, and nature of the image formed for different position of an object with the help of ray diagram. So let us learn images formed by convex lenses for different position of the object. If the object is at infinity, then the image is formed at the focus and size of the image is a point. And nature of image is it is real and inverted. If the object is kept beyond 2f1, then the position of image we will get between f2 and 2f2. The size of the image is smaller than the object and it is real and inverted. If we keep the object at 2f1, we will get image at 2f2. Here the size of image is same as that of the object and it is real and inverted. If we keep the object between f1 and 2f1, we will get image beyond 2f2. The size of the image is larger than the object and it is real and inverted. If we keep object at the focus at f1, we will get image at infinity. The size of image is very large. It is real and inverted. If we keep the object between f1 and O, the same side on the same side of the lens as that of the object, we will get very large size image and it is virtual and erect. Now let us learn how images are formed by the concave lenses. We can obtain the images by concave lens by using following rule. Rule number 1. When the incident ray is parallel to principal axis, the refracted ray, when extended backward, passes through the focus. Rule number 2. When the incident ray passes through the focus, the refracted ray is parallel to the principal axis. The image formed by the concave lens is always virtual, erect, and smaller than the object. If we keep the object at infinity, then we will get image on the first focus, that is f1, which is of point size and it is virtual and erect. If we keep object anywhere between the optical center O and infinity, then we will get image between the optical center and focus f1, which is smaller than the object and it is virtual and erect. Now let us learn the lens formula. This formula gives the relationship between object distance, image distance, and focal length. And the formula is 1 upon f is equal to 1 upon v minus 1 upon u, where v is the image distance, u is the object distance, and f is the focal length of a spherical mirror. It is spherical lens. We can solve numerical examples based on this formula, but it is necessary to use sign convention properly while solving the numerals. According to Cartesian sign convention, the optical center O is taken as origin. The principal axis is the x-axis. The object is always placed on the left side of the lens. All the distances parallel to the principal axis are measured from the optical center O. Hence, distances measured to the right side of the O is taken to be positive, while the distances measured on the left side of the O is taken to be negative. The distances perpendicular to the principal axis and above it is taken as positive, and the distances perpendicular to the principal axis and below it are taken to be negative. The focal length of convex lens is always positive, while the focal length of concave lens is always negative. The magnification due to lens is the ratio of height of the image to the height of object. The magnification is also related to object distance and image distance by the formula magnification is equal to V upon U. Let us see power of the lens. The capacity of lens to converge or diverge incident ray is called power, which is denoted with letter P. This power of the lens depends upon the focal length. Power is the inverse of its focal length, F, and F is expressed in meter. The unit of power of a lens is diopter. Power P is equal to 1 upon F in meter. 1 diopter is equal to 1 upon 1 meter. If two lenses with focal length f1 and f2 are kept in contact with each other, the combination has effective focal length, which is given by the formula 1 upon f is equal to 1 upon f1 plus 1 upon f2. Now let us learn about the human eye and the working of its lens. There is a very thin transparent membrane on the human eye which is called cornea. Light enters in our eye through cornea. There is dark fleshy screen behind the cornea and it is called iris. The color of iris is different in different people. There is a small hole of changing diameter at the center of the iris which is called pupil. The pupil control the amount of light entering the eye. If the light falling on the eye is too bright, then the pupil contract. If the light falling on the eye is dim, then it widens, means enlarges. There is double convex transparent crystalline lens just behind the pupil. This lens creates real and inverted image of an object on the screen inside the eye. This screen is made up of light sensitive cell and it is called retina. The cell get excited from the retina when the light falls on it and generate the electrical impulses. These electrical impulses are conveyed to the brain through optic nerve. The brain analyzes this signal and convert them in such a way that we perceive the object that we see. The lens provides the small adjustment of the focal length to the focus of image. When we see the objects which are at very large or infinite distance, the lens of our eyes becomes flat and its focal length increases. When we see the nearby object, the lens becomes more round and its focal length decreases. Because of this, we can see distant object as well as the nearby object. The capacity of lens to change its focal length as per need is called its power of accommodation, which is beyond certain limit. The minimum distance of an object from the normal eye at which it is clearly visible without stress on eye is called minimum distance of distinct vision, and it is 25 centimeter. The human eyeball is approximately spherical and it is of diameter 2.4 centimeter. The working of the lens in human eye is extremely important because lens can change its focal length to adjust, and because of which we can see the nearby object as well as distant object. In a relaxed state, the focal length of healthy human eye is 2 centimeter. Now let us learn defects of vision and how to correct them. Some people cannot see the things clearly due to loss of accommodation power of the lenses of their eyes, and because of defective refraction by their lenses, their vision becomes faint and fuzzy. There are three types of defects in refraction. So let us learn first myopia, which is also called nearsightedness. In this defect, the human eye can see the nearby object clearly, but he cannot see the distant object clearly. In this defect, the image of distant object is formed in front of the retina. There are two reasons for this defect. First, the eyeball elongates so that the distance between the lens and the retina increases. Second, the curvature of cornea and the eye lens increases. The muscle near the lens cannot relax so that the converging power of the lens remains large. This defect can be corrected by using spectacles with concave lens of proper focal length. The focal length of concave lens is negative, so the lens with negative power is required for correcting nearsightedness. This lens diverges the incident ray, and this diverged ray can be converged by the lens of the eyes to form the image on the retina. Now let us learn the second defect, that is hypermetropia, which is also called farsightedness. In this defect, the human eye can see the distant object clearly but cannot see nearby object clearly. There are two reasons for this defect. First, due to flattening of the eyeball, the distance between the lens and retina decreases. And the second is the curvature of cornea and the eye lens decreases so that the converging power of lens become less. This defect can be corrected by using convex lens with proper focal length. Focal length of this lens is positive. This lens converges the incident ray before they reach the lens. The lens then converges them to form the image on the retina. Now let us learn the third defect, that is called presbyopia. These people suffer from nearsightedness as well as farsightedness. The focusing power of the eye lens decreases with the age. The muscle near the lens lose their ability to change the focal length of the lens, due to which the old people cannot see the nearby object clearly. In this case, the bifocal lens is required to correct this defect. In such type of lenses, the upper part is concave lens and correct the nearsightedness, while the lower part is convex lens which correct the farsightedness. Such spect is a bifocal lens spect. Now let us learn the uses of convex lens. The convex lens is used in simple microscope, in compound microscope, in telescope, in optical instrument, and concave lens is used in medical equipment, scanner, CD player, peephole which is in the door, in the spectacles, in the torches, in the camera, in the telescope, as well as in the microscope. Now let us learn persistence of vision. The image remains imprinted on our eyes is on the retina for 1/6 of the second even after the object is removed. That means the sensation on the retina persists for a while. This is called persistence of vision.